Recordings rolling. It's Thursday, October 23rd. We're going to continue on these chapter 6 textbook puzzles, which are due tomorrow. Guys, only the ones that we've done in class. So we've done some of these already, and we're going to do some more today. So just whatever we finish by the end of class today, you turn tomorrow. And then, yeah, as long as you show your work, that you've done all these, so it's going to be going along, put the point there. I do have some FRTs printed. We'll end the week with some FRTs tomorrow. And everybody did get a take-home quiz yesterday, right? Everybody got a take-home quiz. Because there is okay, that'll be due Monday. If you want to point out one little detail about the take-home quiz, it's number 6, which is the first question on the back. There's a couple of satellites orbiting completely different planets that have related masses and radial sizes. The masses of the planets are listed below the planets, and it's an easy detail to miss. I think most people will see it, but it's easy to miss it. So now your numbers are probably different than these numbers because there's lots of different versions. But I just don't want you guys to miss that the map of the planets listed underneath planets. Okay. Okay, so it might be like M and 7M or M and 6M or M and 8M, something like that. Okay. And tomorrow will be pep rally. We'll be on the pep rally schedule, so all the classes will be shortened by a few minutes. So yeah. All right, so you guys see what we're doing? All right, so in my earlier class, I was able to do some of these that were starred. So the main topics here are like circular motion, centripetal force, which is basically this right here. It's pretty complicated. And also universal gravitation. Right? Of course, I have a bunch of other posters too, because you can combine these and make orbits and bring angular speed and all kinds of things. Right? Those are the main two concepts. So I got number 10, a 25-gram metal washer. So all the way at the bottom here, number 10. 25-gram metal washer tied to a 60-centimeter long string rolled around in a vertical circle at constant speed of 6 meters per second, which is actually a strange detail, but here, hold on to that. I'll come back and talk about that later. Calculate the tension in the string when the washer is at the bottom of the circular path, when it's at the top of the path. So I definitely want to draw that out. So number 10. Can you guys on your paper also draw a circular path? A circular path drawing? Okay, so there's some washer that's going around. Or a little washer. Okay. At some point, the washer is at the top. At some point, the washer is at the bottom. You guys said there's some string. Well, everybody does have a ruler nearby, right? Have a ruler. Okay. So yeah, it's good practice to draw straight lines with rulers. Like I know the string is going to be a straight line all the way around. Okay, something like this, and this. Okay. And this washer is flying around with some speed. Right? Washer has a mass of, it said 25 grams, and somehow a constant speed going around of 6 meters per second. Oh, and the radius of the string they gave also. Radius equals said 60 centimeters. Well, they said the length of the string, but you guys know that would be the radius of the circle, right? Okay, so that's your given values. Okay, I think there is actually one more value you have to know that they did not explicitly tell you. What else do you think you'd have to know?
Gravity?
Yeah, gravity field. What do you guys feel like using for gravity field today?
9.8.
Oh, I heard 10 first. All right, let's see that. 10 meters per second squared. All right, first come, first serve, but not how about this? Because the values that they gave you, well, meters per second is fine. That's based on SI units. But what about grams? Because to plug numbers into some formulas, you don't want mass in grams. You want mass in what? Kilograms. So let's put that in kilograms. Guys, how many kilograms is that?
Wait, how many grams is that?
25 grams. 25 grams. Yeah. Guys, kilo. Kilo is a factor of a what? 1,000?
Yeah.
It's like 3 decimal places. Can you guys roll back the decimal in 3 decimal places? 0.025 kilograms. Okay. So that's the number we'll actually end up feeding into the calculator at some point. How about the same thing for radius? Radius 60 centimeters. I know that's a little over half a meter stick, if you wanted a visual on that. So how many meters would that be? 0.6 meters. Yeah. Okay. So now we have all the values in base SI units. You guys think I should make a free body diagram on the washer? Now, some points at the bottom, some points at the top. The questions for each of those. Okay. So let's start with the bottom. Okay, so let's do a free body diagram right down here. what's one force on the washer right at this moment? Yeah, its own weight is pulled straight down. Actually, you know what? I don't want to make that very long. I'm gonna make this a little shorter. All right, a little wide out here. Hey, my picture won't be exactly to scale, but I don't want it to be like too crazy far off. So let's call this mg right here. So here's my mg. Okay. Oh, and since you know mass is 0.025 kilograms, and g we're going to call 10 meter per second squared, what would m times g work out to be? Yeah, 0.25. And what's the unit? Newtons. Oh yeah, newtons. Okay. Now, if this washer, I guess they go going clockwise, so here we'll be going directly to the left just for one moment. It's going to be here, and here it's going to the right. This moment, it's going to be here.
It's a moving speed.
Guys, what's another force on this washer down here? Tension. Tension. Is which way does the tension pull? Up. Right. You guys would do you think the value of the tension would be equal in magnitude to the weight, or smaller than the weight, or larger than the weight?
Larger.
Larger. I can imagine that. Here, you guys think if you took one of these spring scales and like actually hooked a weight to it and said, okay, this weighs, whatever weighs, right? And then start swinging around a circle, right? You think the tension would go like, and be like really, really big? That makes sense, right? So let's put a big old tension force right here. Big old tension. Now I'll call this F sub T bottom, because later we'll find F sub T top. This is when the washer's at the bottom. You guys got that? Okay. Yeah. Oh, so notice I made the tension larger than the weight. So is there a net force on this washer? Yeah. And that net force you could also call the what force? Centripetal. Aha. Right, so store that away for later. That would help them. Now, eventually we'll also do this analysis at the top. So, guys, at the top, does the washer have the exact same weight that it did down here?
Yep.
Yeah. Okay, so, same magnitude as before. Mg, 0.25 newtons. Right, that didn't change. But what about the tension? Now, which way does the tension pull? How about downward? Ooh. Okay. And if you had to guess, or maybe you have a pretty good intuition, how do you think the tension compares to the bottom tension? The top tension is what? Yeah, I would say not as much. Okay. Now, how does it compare to this weight? Well, that depends how fast it's going around. So I'll call this FT top. Okay. Is it possible this FT top actually goes all the way to zero? Guys, could this tension be zero at the top? Could it be? Show of hands. How many guys think that, the tension could possibly be zero at the top? Yeah. In fact, I have a poster for that. Oh, it's this one right here. Okay. Guys, if this tension goes to zero at the top, FT top is zero, then would this just barely get around the top? In fact, you could use that to calculate the minimum speed, which always works out to be this expression. Oh, let's try some of this. Now, in this case, well, there is tension, so, or I think there would be, right, going around this speed. This is pretty good speed. No, I don't know right away if the tension is more than or less than the weight. I'm guessing it's probably more than. Right, that gets apart. Okay. Now, also, before we get chugging on formulas, there's one more detail I want to point out. You guys see the speed of 6 meters per second? Okay. Now, they specified that it's constant speed all the way around, constant linear speed. They specified that. Okay. Realistically, do you think that would be a common expectation? Or do you think it'd be more realistic that as the washer is headed down and gravity's pulling down, it's actually speeding up? How many of you think that if they didn't specify otherwise, you would expect this to speed up on the way down? Who thinks that? Yeah. And then when the washer crosses this lowest point and it starts moving kind of upward-ish and gravity's still pulling down, I mean, I think the washers should be slowing down. Yeah. Right. And the only thing that would override it is that they specify otherwise, which they did right here. They said it's a, they said constant speed, right? Now AP sometimes also does that. They specify a constant speed, right? But starting next week when we get to conservation of energy, we might also see this type scenario. You should naturally expect it to speed up on the way down, slow down on the way up. Okay, so with all that, we got to find these two tensions. So, let's start with the bottom tension. So this bottom tension. Who can think of an expression you could set up that could eventually solve for this bottom tension? These two forces Are they sort of adding or subtracting from each other? Subtracting? Could they subtract and provide some kind of net force? And then net force, which allows a washer to move on a curved path, could be called a what force? Centrifugal force. Could that be the first domino in a series of dominoes that leads to the answer? Right. So this net force right here, you could write as what minus what? Yeah, Ft bottom, which we're solving for, minus mg. And that results in what fraction on this side?
MB squared over.
Yeah, mv squared over r. Yeah, isn't that true? Is that okay? You guys can come up with that, right? Oh, you know what? Looks like we're solving in terms of variables. We just got one algebraic step. Can I just very simply add over the weight? Can I do that? Add over the weight. So I'm going to say Ft bottom equals mv squared over r plus mg. Isn't that true? Right. Oh, can you just plug in all the values? Can I do that? Here's mass, 0.025 kilogram. Here's G. Here's V. Don't forget to square that V. Then here's your radius. Those are all in base SI units. Can I just pop all those in? Ft bar. Here, I got enough space on my paper to write the numbers. So 0.025 kilograms times 6 meters per second. Square that. Just the speed. Divide by 0.60. I know I've got tiny font going on, but basically. Oh, actually, no, I know what mg is. It's this right here. 0.25 newtons by itself. That's that. Okay, so plug that in. We get yeah, might even have a little more space. So this is actually 1.5 newtons plus 0.25 newtons. Okay. And actually by doing that, you can pretty quickly see what is the tension compared to the weight. What is the tension compared to the weight? It looks like 6 times as much. It's just how it worked out. You guys see that? Okay. So guys, my picture, if my picture was to scale, how long should I have really drawn this tension vector compared to this weight vector? How many times as much? How about 6 times as much? Right, 6 times as long. Right, if it was truly to scale. Right. But anyway, put it all together. I mean, the tension force at the bottom is 1.75 newtons. Does that look right? Guys think? Right, guys good? You guys ready to find the tension at the top? Tension at the top? Yeah. All right, let's do that. I bet I can start with the same original domino set up here. The net force is the centrifugal force. F net equals centrifugal. But this time, guys, at the top. How do you write the net force from? Yeah, you have to add these two. Because aren't they conspiring together? They're both pulling down. The tension's pulling down. The weight's pulling down. They add together. This is Ft top plus the weights. And that results in mv squared over r. Okay.
Oh yeah.
Good. All right. So then Ft top, which we're solving for, would be mv squared on r minus the weight. Okay. Oh, you know what? I have values for each of these already because I got them right here. I know this comes out to 1.5 newtons. And this here comes to 0.25 newtons. So should that be Ft bottom or top? Ft top is I think it's 1.25 newtons. Right? You guys think so? Yeah.
So, I'm still confused. What did you think you get?
At the top setup? Okay. So as this washer flying across the top, there's 2 forces on it. Its weight's pulling straight down, but the tension is also pulling straight down. So they're conspiring together. So can I just add those 2 forces together? That's exactly what this is. So it's the tension plus the weight. And then what they're forcing this washer to do is to move on a curved path. So they're acting as the centrifugal force, which is in square root of R. Right? Right. Then you can subtract over the weight, and that leads to the top tension. So Ft top equals this minus this, like that. Okay. And I know what mv squared over R is. I found it right here. It's 1.5 newtons. I know what mg is. I found it right here. 0.25 newtons. Okay. So at the bottom, it turned out that we had to eventually add those together, and at the top, it turns out that we eventually subtract those. All right, yeah. So I will.
I did see the value for me.
Yeah, I will. Of course, post this video later.
Okay.
Yeah. Second look at it. All right.
You need some graph.
Yeah. You can always sit closer too, or yeah. Wow, so that's good. All right, let's go. But good. Oh, yeah, thank you. Let's have some gravitation, and if we have time, we'll go back to this amusement park ride. Oh yeah.
What were all the questions that we've done so far?
Okay, so the ones I got marked, I think the ones we've done already is number 2, an airplane is traveling. Number 9, an object on this table. And we did down here a different number 9. We did a point on a turntable. Some friction going on. We did those. Okay. We just did number 10, the metal washer. I think it's all we've done so far.
We did 20.
Did we do
Yeah,
number
we did 20 on the other side, on front.
number 20 on this side?
Top right.
Oh, we did number 20?
Yeah.
All right. So number 20.
That was on the 9.
Yeah. All right. Thanks. Keep track of that. Circle that one too. Oh yeah.
What was it?
What was the answer?
Yeah,
Okay.
Anderson.
So number 10, the tension at the bottom came out to 1.75 newtons. The tension at the top came out to 1.25 newtons. All right. Right. So we got to hit some gravitation questions. Right, so let's do the very last question, number 32. All right. Well, you guys work backwards here. The ones that got started. Number 32. 2 satellites are in stable circular orbits around the planet. One is at radius r sub a, and the other is at radius r sub b, which is twice as far out as the first satellite. Yeah, guys, twice as far out. Is that twice far out from the surface or from the center of the planet? From the center. Aha, from the center. Calculate the ratio of the speeds of the 2 satellites, and also the ratio of the time periods. We're gonna do all that. Do all that. So let's get a picture going. 32. So let's get a planet. There's a planet. Okay. And we've got a satellite. Now this satellite is at some. Well, oh, here, I'll draw its path. It's on this path right here, which is at r sub a. Okay. Then there's another satellite twice as far out. Now I've got this one as being about 4 centimeters out, so I need to go 8 centimeters, which is like right here. Get another path going. Another satellite. This is satellite B. So satellite A, satellite B. Okay. Now this is radius B, which is equal to 2 times radius A. Okay. Right. So yeah, 32. Right. Looks like that. So yeah, so just to emphasize this point, you guys see that these radial sizes are relative to the center of the planet, not the surface, but the center. Okay. Now each of these has an orbital speed. So here's speed for A, and here's speed for B. Okay. There's also some time period it takes each of those to go all the way around the planet. Make 1 revolution. All right, you guys got that set up? Oh, guys, they never gave you the masses of the satellites. Do you need those? Nope, doesn't matter. Has nothing to do with anything. Right. Here, I'll give you guys a head start before I write anything else. See if you guys can figure out any way to make any progress on that. I'm gonna take a trip around the room and give you guys a head start. There's actually more than one way to start, but see what you can figure out. Yeah. That's a good thing to know. Yeah, that's a good thing to know. Yeah. I think you guys are coming up with some good ideas. Now, I think because the whole question here is about ratios of speeds and time periods. I think the first person in history who could have figured out any of this, his name was what? Kepler. Kepler. You guys remember these right here? Guys, isn't this maybe something to do with Kepler's third law? Maybe.
No.
Right? You could do Kepler's third law. Actually, I'm going to take you guys through a different method, though. How many of you guys remember how to derive orbital speed? Orbital speed. Actually, that's what I want you guys to do. Guys, go ahead right now. Derive orbital speed from scratch. You guys got to be able to do this for the AP exam. Everybody's got paper within reach. Yeah, guys, let's derive orbital speed from scratch.
From scratch. Where?
Velocity or the square root of
Everybody's derive the orbital speed from scratch.
and then we use that. And then you have your radius of the third.
So maybe it would be helpful to have a free body diagram on the satellite. Okay, so this satellite have a weight pulling straight this way, F sub g, gravitational force. Is there any other force?
No.
No, just that one. Okay. And that gravitational force is acting as a what kind of force?
Gravity.
Centripetal. Boom. Here's your first step. Centripetal force provided by universal gravitation. Okay. So guys, what's the formula for centripetal force? Yeah, inverse squared over r. Good choice. Now, how about universal gravity? How's that go? GMM over r squared. So you guys can do that. Okay. And then, what cancels out at that point?
Mass.
Mass of the satellite, but not the planet, of course, just the satellite, and one of the r's. Can you solve for v? And you'll always get this expression right here. Now, if you get to an AP question that's multiple choice and you have this memorized, you just pull this out of your back pocket and solve it. If it's a free response question, I would expect to have to derive that from scratch, just like that. 3 steps though.
Do we have that formula right there? Would we have that? And do we just have to arrange the variables?
Yeah. So guys, it's these 2 yellow formulas right here. So this top one is universal gravity, GMM over distance squared. And this bottom one is actually centripetal acceleration, just v squared over r. But if you jump straight to centripetal force and v squared over r, they'll accept that. So that's fair. Yeah, so those are on the AP equations. All right, so got that. So you guys got centripetal force provided by gravitation, mv squared over r equals gmm over r squared. So v for circular orbit, square root gm on r. Okay, got all that. All right, now first we got 2 satellites, and the first question was, what's the ratio of the speeds? Oh, well, I could do this for satellite B and for satellite A and see what happens. So the speed for satellite B compared to the speed for satellite A equals, I got square root of if they're orbiting the same planet, right? So m is equal to m. And of course, capital G is capital D, that's universal. Okay. But I'm going to make this radius A for speed A. Okay. And guys, radius B is actually what in terms of radius A? 2 times. Yeah, it's be like that, wouldn't it? Right, guess yet? But what's about to happen? Bing. Then can I cross multiply the b sub a?
Yeah.
So bb equals 1 over the root 2 b sub a. Okay. Could you also do this? Could you call it root 2 over 2 b sub a? Is that the same thing? Or 0.707 b sub a. Those are all the same thing. It's all the same thing. So the speed of the satellite that's further out, that's twice far out, is about 71% as fast as the one that's closer.
Yes, sorry.
Right, you guys see that?
Yeah.
Alright, how about time period? Time period.
Mr.
Okay.
When you after you were done canceling out, you just got rid of VA and was left with VB, leaving just one over square root two.
Yes, I have VB over VA. And the only thing that's left over here that didn't cancel out is this 2 that's in the denominator in a square root.
Yeah, so it's like sort of one out.
Yeah, so it's 1 over the root 2.
Yeah, and so then the VA under V1 just goes away.
I cross multiplied it over here.
Oh.
Yeah. So I said, what is VB in terms of VA? Yeah, so I just cross multiply the VA. Alright. Alright, how about time period? There's different ways you could do this, but what I might think is this the time to go all the way around what they're calling a circular path. A circular path. Right. Well, we got a bunch of radii floating around. Because what is the distance around a circle called? It's called one circumference. Aha, circumference. So, could you guys say that? Let's see. Is speed distance compared to time? Right. And the distance around a circle is what? 2 pi r. And then here's time period. Okay, something like that. Now, the second question, we were supposed to solve for time period. Ooh, guys, can you solve for time period in terms of radius and speed? Cross multiply the t, divide down the v. I think the time period to go around would be 2 pi r is the distance, divided by the speed you're going at, v. Okay. So that's a general expression that can apply to both of the satellites. And then what we'll do is we'll plug in the corresponding values. Okay. What's radius, what's v? Right. We'll get everything in terms of satellite A. Okay. Everything in terms of satellite A. All right, guys, ready to do that? Are you guys good with how I got this so far? Okay. All right, so let's do that. Let's say I want to know what is the ratio of time for satellite B compared to time for satellite A. Isn't that exactly what they're asking? Or what? How they phrase that? Oh, actually, they did phrase these both as ratios. Oops, I forgot that. Okay, whatever. All right. They are looking for exactly this. So that'd be. So let's start with satellite A. Okay, we're gonna do everything in terms of satellite A. So it's 2 pi radius A divided by speed A. Yes, that looks good. That would be the time for satellite A to go around. Is that right? Now for satellite B, I could write the same expression except with subscript b's, but I know what radius B and speed B are in terms of radius A and speed A. 2 pi. Guys, instead of radius B, I'm going to say what in terms of radius A? Radius. 2 times. Guys, isn't radius B twice radius A? You guys remember that? Everybody follow that? Okay. And then, what is speed B in terms of speed A? That's this right here. Yeah, 0.707, 1 over the root 2, however you like it. So, how about I do 1 over the root 2? Okay. And that's times speed A. Oh, now I have lots of fractions within fractions. Can you guys handle fractions within fractions? Okay.
Yeah.
Here's the thing, I'll put a little thought cloud over here. Is if I have A over B all divided by C over D, like a fraction within a fraction. Is that the same thing as A over B times what or what?
D over C.
D over C. Yeah, right. Okay. Flip and multiply kind of thing.
Yeah.
Okay. So, I think we can use that cleans up. Here, I'll do that first before I start slashing. TV over TA is okay. So I got a 2 pi. I got another 2. I got radius A. Guys, 1 over the root 2. Can I actually just bring that up to the top as the square root of 2? Is that okay? And then I still have a VA down here. And then times, and then down here. So I'm going to flip and multiply this one. Got VA. Comes up on top. And then there's a 2 pi and a radius A. Okay. So I just do a little shuffle with arithmetic. All right. You guys ready to slash and dash? Oh, yeah.
Oh, okay, if before you do that, if you go back to up there when it's fraction over fraction, could you start canceling out from there?
Oh yeah, these are good. Yeah.
Okay.
Yeah. All right. All right, here we go. I think I'm left with 2 root 2. Is that it? 2 root 2?
Right.
That also? Okay. So the answer is 2 times the square root of 2. Okay. And if you want a decimal value, that'd be 2 root 2. 2.83. Okay. So you could also say this. Time period B equals 2.83 times time period A. You guys finish writing that right there. Yeah, we saw that a little different earlier today, but I got the exact same answer. All right. You guys good on those 2 satellites? You guys ready for Jupiter? It's Jupiter time. Number 26. The 4 largest Jupiter's moons are listed in this table. Using this data to complete this table, okay, so we got Io, Europa, Ganymede, and Callisto, 4 moons. They say what's the semi-major axis, and they say let's treat the semi-major axis basically as a radius. And these orbits are slightly elliptical, but we're gonna estimate them as approximately circular. Okay? And there's some orbital period in Earth days. Okay? They want you to finish the rest of this table and also find the mass of Jupiter. Okay, guys, let's just find the mass of Jupiter, and well, like once you have that, then you apply the same math and figure out everything else on the table. Okay. So we're gonna find the mass of Jupiter. So number 26. Get a picture. Got Jupiter. Okay, you guys got Jupiter, and here's Io. Io, bing, and Io's going around. Got a circular orbit. Okay. There you go. So they told you the radius of this axis. So say R radius for Io is 421,700 kilometers. And they say the time period to go around, I'll write that up here, is 1.769 Earth days. Okay. So we're based on Earth, we're looking through a telescope, we're watching Io go around, and from our point of view, say, oh, it took 1.769 days to go over. Okay. You guys get all that? There's another number you need to know to be able to solve this, and they did not explicitly type here. Do you guys know what other universal gravity constant? Yeah. You guys remember? Here, I'll write right here. Capital G is 6.67 times 10 to the negative 11 meters squared per kilogram squared. I'm pretty sure we're going to need that too. Okay. All right, so we got all this. Okay. Now, guys, kilometers, days, those don't sound like base SI units. So let's turn this into base SI. Let's turn this into meters. Ooh, guys, is this like 4.2? You guys, everybody following? Really here? Guys, is this 4.2 times 10 to the what kilometers?
3.
1, 2, 3, 4, 5. Like 4.2 times 10 to the 5. Right. So how many meters would that be? That'd be like 10 to the what meters? Huh? Guys, going from kilometers to meters. That's a factor of
3.
3 decimal places.
Yeah.
Right. On top of the 1, 2, 3, 4, 5 that's already here. Yeah, that's like 4.2 times 10 to the 8 meters. Right? 10 to the 8 meters. Or however you write it. I just want to do a little scientific notation there. And then how about days? Let's turn this into, guys, when we get to calculation, we don't want time in days, we want time in what? Seconds. Okay. Now this is all in terms of Earth time. So 1 day would be equal to what? 24 hours, 1 hour, 60 minutes, 1 minute, 60 seconds. Seconds. Bing. 1 point.
I think these are-
9. Got 24, 60, 60. I'm looking at 152,842 seconds. That's a lot of digits, precision, or 6 digits. We'll just run with the number. Let's see what happens. Great. You guys good so far? Right. So I got to make sure I got this set up. I got all the values I need. I did some conversion to get everything baseless ideas. Okay. It's all just part of the set.
I agree.
We got it set up. Now the question is, what is the mass of Jupiter? What is the mass of Jupiter? So, now there's more than one way to do this, but to kind of guide you guys through and it's sort of a standard way to do it. Okay. Let's play out. How about, guys, what was your setup for orbital speed? What might have you guys derive orbital speed from scratch? Yeah, you guys remember we did, you guys did gravitational force provided by centripetal force. So G M M over R squared equals MB squared over R. Okay, guys remember that? Okay. Guys, what does this little n represent in the context of this story? Mass of Io. And one of the radii side. Okay. So I got this. Okay. Now, our quest right now is to find the mass of Jupiter. So that's this one right here. Isn't that this big M right here? You want to find that? So let's go G M we're solving for divided by R equals V squared. But guys, instead of V, I'm going to write this as an expression, something else squared. Distance over time. Guys, isn't speed equal to distance over time? Okay, this is a method you've used before in labs in this class. Like the Plato lab. Here, guys, folks here. Because isn't it true when your Plato canister is flying around, you measured the radius of that circle? You guys remember taking a meter stick and pulled it up there? And you had the stopwatch right here, and you timed. Okay. And then you said, well, the speed would just be the distance around, which is what in terms of radius? 2 pi r. And then the time, I'll call it capital T for time period. Is that okay? That's what speed would be?
Yeah.
All right. So here, next step. Actually, here, can I cross multiply this r and divide down this g? Can I do that? So the mass of the planet equals, so I got a 2 pi being squared here times r squared times the third r. So isn't that like r to the 3? And then I divide down this g, and I got that t down there. Okay. I think that's the answer in terms of variables. Because that expression right there, will that find you the mass of any planet that has a moon going around it? I should do it. Beck, I think that looks familiar. I think I've seen that somewhere before. Have you seen that somewhere before? Where have I seen that before? Hey! It's the same thing! It's been there the whole time! It's right behind you the whole time. You got your very first day of school. God, so now we just gotta plug the numbers in. Let's plug the numbers in.
Mr. Griffin.
Oh yeah.
Your poster is different than your equation.
Huh? How so?
It shows gt squared and yours doesn't.
It does. Yeah, good catch. Good catch. Guys, you guys catch that too? How's this messed up? T squared. Good call. T squared. All right. Saves. Thanks. All right, let's plug that in. Okay, so here, working from here. Right. So going mass of Jupiter is I got a 2 pi quantity squared. Now this r is, well, we found that right here. It's 4.217 times 10 to the 8th. That's meters. Okay. That's all to the power of 3. Okay. And this is all divided by I got 6.67 times 10 to the negative 11. That's Newton meter squared per kilogram squared. So remember, these are all based on SI values, so all the numbers will be consistent. And the time period, that's what we found up right here, 152,000 seconds. So 152,000, and then 842 for these seconds. This is all grouped together in the denominator. I think if I feed that expression into the calculator, whoops, squared. Don't forget to square the time. Gotta square that time. There we go.
All of those, like,
Square that time.
the imaginary, it's funny about.
That should give me the mass of Jupiter. Okay. So the last step is, can you correctly plug this into the calculator? Can you communicate with the calculator? And it's important that you get all the parentheses correct, and you get the correct exponents on the correct group of parentheses and so on, and the correct fractions where they go. So here, I'll plug it in front of you guys so that you can follow along with me. Guys, see if you guys can correctly plug this in. So that's last test right here. Can you correctly plug this in? So I got a 2 pi and then close parentheses there. So open parentheses 2 pi close parentheses. I'll square that. Then open a new parenthesis. 4.217 times 10 to the 8. Close parenthesis there. Power 3. Then divide by. Then open up some more parentheses because everything else is down the denominator, so I don't want to close too early and accidentally stop dividing. 6.67 times 10 to the negative 11. Close open. 152,842 squared. Okay. You know what? Before I hit enter, I'm going to Google the answer. We're going to see. We're going to find out. Come on, give me Google. What is the mass of Jupiter? Okay. Oh, it gave it to me in kilograms. Of course it did. Guys, you guys see 1.9 times 10 to the 27? You guys see that? 1.9 times 10 to the 27? We're going to find out. Come on. Oh, yeah. 1.9 times 10 to the 27. That's kilograms. Oh, yeah. We are winning. Bing. All right, guys, good? Alright. How about you guys, since we only got so much time, we have enough time to solve one more. But the rest of this table, guys, could you, if you want to, now that you know the mass of Jupiter, do you think you could kind of do some really similar math and solve for the time period or the radial distance of these other moons? Right? And do you think, guys, books here. What if you took the ratio, every single row in this table, if you took the ratio of the time squared compared to the radius cubed, do you think you would get the exact same constant all the way down? Yeah, and that's what Kepler would have said too. Yeah. All right. Oh, hey, look at this. This would have too. Okay. That looks like that. There's right there. All right. So last one we'll do. Last one is number 25. Amusement park ride called the Rotor. Debuted in 1955. I'm gonna get back to 1955. In Germany. Passengers stand in the cylindrical drum of a rotor as it rotates around its axis. Once the rotor reaches operating speed, the floor drops, but the riders remain pinned against the wall of the cylinder. Hey, was this a good question yesterday? I think it was. Suppose this is rotating at 25 revolutions per minute, has a radius of 3.5 meters. What's the minimum coefficient of static friction on the rider to make sure that they don't fall out? Yeah, 25. So let's get this going. Here's the rotor. Like this. This guy right here going around.
That's as well.
Okay, so it's rotating around. Like that. They said this is 25 revolutions per minute. And this radius right here is 3.5 meters. Is there anything else? Well, I'll give you guys gravity field. We've been using 10 meter per second squared. Stick to that. Alright, so is that okay? That's it? Okay. Now let's do a free body diagram on the sky. Oh, you guys have to go a little fast. I'm gonna beat the bell. Here we go. Does this guy have a weight pulling straight down? Does this guy have a normal force pushing which way? Inside F sub n. Okay. And how about guys, what force is keeping this guy up? Oh, yeah, sorry about that. Thanks. Please fix this. Hey, where's my camera? Where's my camera? No, there's usually a button here I can click. Anyway. All right. Well,
Just not do that one.
no, not that one. Let's try this again. Okay, reopen this application. There's usually a camera switch off down here. Yeah.
We could just finish it tomorrow.
Well,
We can do that.
yeah, I think we're gonna run out of time. Okay, I'll have to fix that. All right, well, let's close that up right there then.